Good afternoon, you all. So this is our day 2 uh, program on faculty development program on emerging topics in computing, quantum, microfluidics, and memristors. Today we are in the last session of our quantum computing track. So in this session, Dr. Kamalika Datta will share with us regarding synthesis and optimization of quantum circuits. Dr. Datta. City, Kolkata, India. Earlier, she worked as a postdoctoral fellow at National Technological University, Singapore from February 2019 to September 2020. She completed her BSc Computer Science from Reversible College, Kotak in the year 2003, Master of Computer Application from Biju Patnaik University of Technology, Bhubaneswar in the year 2006, Master of Science degree from Indian Institute of Technology, Kharagpur in 2010, and PhD degree from the Indian Institute of Engineering, Science and Technology, formerly Day-2, Sipur in 2014. She has guided 2 PhD students and published more than 75 papers in peer-reviewed journals and conferences. She has successfully handled 3 research projects sponsored by DST Government of India, and have visited Germany and Austria several times in connection with joint Indo-German and Indo-Austria projects. She has also offered 2 SWAM NPTEL courses on computer architecture and organization and embedded system design with ARM. Her research interests include reversible and quantum computing, resistive memory systems, and information security. She is a member of the IEEE. So now I would like to ask Professor Datta, or request Professor Datta to please continue your talk.
Thank you very much, Dr. Kole, for the nice introduction. So I will start my talk. Let me share my screen first. Is my screen visible?
Yes, it is visible, ma'am.
Okay. Okay, so I welcome you all to this post-lunch session of day 2 on this FDP on emerging topics in computing, where I specifically will be talking about quantum computing. And specific to that, I will be talking about some of the synthesis and optimization method. Although the talk will be on synthesis, but the first step that I want to do today is to make the participant aware of what we have discussed so far, such that you have a grip of like what has been discussed in quantum computing. And the next step is, and probably the final step, where we identify some of the research problem. So the idea of this FDP was, of course, to make aware you of the essential technical details from the basic, and then let us introduce you with some problems where you can work upon it and find out solutions for the same. Okay, so with that, this is how I will go ahead. I will first discuss about what we already know. I'll just recapitalize that once more. Then I will be specifically talking about synthesis. Synthesis means how do we design these circuits? We have been talking about circuits from day one, but let us see actually how do we design those circuits. Of course, when we design that circuit, we will go later and see that we don't design circuits for very large ones using just quantum gates. Rather, we use one level of abstraction there. Why we do this? We will talk about that in detail. And also, Dr. Kole mentioned this in the morning, that when we design a circuit in our conventional computing, how do we do that? Think of an adder circuit. If you want to do the design of an adder circuit, you will definitely not start with the transistor. You not pick up transistor and start doing it. Rather, you will be provided with some gate library, NAND gate library or NOR gate library. Using that, you design circuits. And once you have that design, there are other tools to do that routing and placement of your circuits on in transistor level. Same with this. So we will be seeing that instead of doing synthesis using quantum gates, we work on one level higher, that is reversible circuits or reversible gates. So we will be using those gates to realize those functions. And we have seen in the previous talk where those functions can be plugged in as an oracle within the whole set of quantum algorithm. So within a quantum algorithm, there are portions which needs synthesis. And in that respect, we will be seeing some of the simplest synthesis methods that are there in literature. But again, whatever I will be discussing, there is a lot you can take up from that discussion and you can work on some other domain, or you can identify some problem from there and start doing your own synthesis for certain functions. Okay, so this is how we will be going ahead. Now, to recapitalize and to again remind you of something is just keep two things in mind when you start working on quantum computing. If you are already doing it, you have to remember this. And if you are starting it, please remember these two things. First thing is that quantum computing is aimed at solving some computationally difficult problems. What do we mean by that? So we have been seeing from day one yesterday that we were talking about algorithm like Shor's algorithm, Grover's algorithm, and which claims that if we can actually implement those algorithms in quantum domain, then we will be able to achieve some kind of benefits that is not possible with our classical computer, right? So there are certain instances of problems like search and many other problems where efficient classical domain algorithms are missing. And for that reason, quantum computing is aimed at solving those computationally difficult problems. Now, also one thing you have to remember and you have to appreciate that our conventional computing has come a long way, isn't it? And we have got enormous benefit, and we are getting whatever we are doing. Even what we are doing today is that conferencing with all people, conducting FDP, conducting all the classes that we do. Everything is possible because of the advancement in the conventional computing technology, and each day that is advancing. So do not confuse that that is going to be replaced by quantum computing. No, that will not happen. So quantum computing will not fight to compete with the classical computing for those particular problems which can be efficiently solved using quantum computing, classical computing. So let those problems that are already solved by classical computing, very good. We are mostly interested into solving certain difficult problems for which the classical computing either takes too much time or the solution is not possible. So this is a very clear thing that we are going to have quantum computing for specific tasks. I believe this has cleared up all your doubt that where quantum computing will come into picture. Now, to proceed with, I will show you this diagram. So generally, the proposed computational model will be somewhat like this. We will be having our conventional processor. We have memory. So we have this conventional computing running all the time. And for certain tasks for which this conventional computer might not give a result in stipulated time period, we will take the help of quantum coprocessor. So if you see this quantum coprocessor will come into picture for specific problems and not for general purpose problems. And also one thing, we should not think that tomorrow we will have quantum computer and we will be buying one. No, that is also very difficult. Why? The technology using which the quantum computers are built, they require some specialized environmental constraint. They require very, very low temperature. You need to maintain very low temperature there. A very small bit of noise can tamper a lot of other things. Okay, so there are some environmental constraint, and because of that, we will not be using that as if it is somewhere in our home and we are using it. It will be there somewhere in the cloud. It will be there somewhere in the cloud. Fine. So the quantum coprocessor will be there. We need quantum algorithms. We need quantum circuits. We need reversible circuit, everything. But all will be somewhere in the cloud, and we will be sending our request, getting processed, and we will get the response. In the same way, we have seen in the morning how Dr. Shahu has shown us with a IBM QX machine, which is available in cloud, how we can execute smaller function, right? But we want to scale this up. Of course, scaling this up will come with a lot of technological challenges, lot of fabrication challenges, lot of errors are there. So we have lot of challenges, right? So challenges will be there. But to this end, one thing is clear, conventional computing will remain here. Quantum processor will be there and will be there in the cloud, where using this conventional processor, we will be using quantum processor as co-processor. It will be solving certain problems which are difficult for conventional processor. So with this, I will not spend much time on this because we have discussed about this a lot. Just to again recapitalize that superposition and entanglement are the two very important phenomena, quantum mechanical phenomena, that must be possessed by that device, by that qubit. And then only whatever speed up we are talking about, whatever possible algorithms we are talking about that could be run in that device is possible. Fine. So quantum mechanical phenomena of superposition or entanglement, superposition and entanglement are very, very vital. We have also seen this, that a collection of n qubits can be in arbitrary superposition of 2 to the power n different possible state. So for 2, it will be 4, for 3, it will be 8, and so on and so forth. And it allows massive parallelism in computation. Why? Professor Shahu has beautifully explained in the morning that why this parallelism, how this parallelism we are able to do because of the superposition feature. superposition phenomena that happens. But apart from everything, the final thing is the measurement when we want to know the result. Just think of the number of gates if you are having. Suppose this is a NOT gate followed by a NOR gate. Then let's say we have an AND gate like this, right? So these are all built up using transistors, right? These are some gates which are built up using transistor. Now you see what is happening is that in this case, we apply certain inputs. We apply certain input here. Step by step, we get certain output. And finally, we get the result. And this is our result, right? But in quantum domain, what happens that whatever in between you have, and here there is either 0 or 1, right? In classical domain, this is the thing. We have either 1 or 0. But in quantum domain also, after this measurement, what happens is that it collapses the system of this n qubit, whatever n bit you are having here. It collapses that into one of those 2 to the power n inputs. So even if you have this, many possibilities, but ultimately we will be choosing the one with some probability, right? So this is basically how do we actually differentiate to an extent how the conventional computing happens and how the quantum computing happens. With this, I'll discuss this very briefly. The most important thing here is that all quantum operations are inherently reversible. So this reversible thing is very important. We have seen in the morning today that the oracle function that we can realize, that Boolean function that we realize, it has to be reversible. And we have seen this in the morning in Dr. Kole's talk that every quantum operation can be expressed as a unitary transformation matrix. And all of this matrix for a single qubit, you can represent it as 2 cross 2 unitary transformation matrix. And for a 2 qubit, you need 4 cross 4 and so on and so forth. But the in thing here is that all quantum gates or quantum circuits, it has to be reversible. And another important thing is that we have looked into gates. We have also looked into quantum circuits. Now, what is the basic hardware? You think of in conventional computing. It is your transistor that is at the lowest level. And what is at the top of that? It's gates. Gates are built using transistors. And at the top level, you have functions. So if you consider, let's say, an adder function. Adder function can be broken up into some gates, maybe using NAND or NOR, anything. And finally, these gates are nothing but transistors, right? In general CMOS technology. In quantum computer, it is little different. How it is different? This is our device. You see this diagram. If you see this diagram, this is the real IBM machine. But these are the qubits, and these are your hardwares. And these hardwares require very low temperature to be preserved. To build 1 qubit, you require many hardwares. Okay, so there are those fabrication constraints are always there. But apart from this, once you have this particular configuration, you see there are arrows going from one end to another. There are arrows coming from here, like it is going here, and so on and so forth. These arrows actually say that which can be your control and which can be your target. This is what is meant by these arrows. So if you see this Q2 is going to this Q0. Okay, so you can operate on this using these two when the control and target is like this. You cannot do the opposite one. So can you see some of the restrictions that you have when you are actually going to the machine? And all these are what? Qubits, like this. These are all qubits like this. And this is our hardware. When we say that we are performing a gate operation, that means we are performing something, let's say, on these 2 qubits. That is our gate operation. When we say we are perform another gate operation, we are performing on these 2 qubits to perform that operation. You have seen Hadamard gate, you have seen CNOT gate, everything, right? So in all those, there are some which operates on a single qubit, some it operates on, let's say, on these 2 qubits, right? So whenever we say that we are performing a gate operation, that means we are performing some operation on these qubits. All right? So with this, I will proceed. So by now, what we know, whatever I have discussed so far has been already discussed in all the previous talks. I have just recapitalized you that, look, we have all these things in place. Now, what is our task in hand to do? What are the research challenges that are there when we have to run an algorithm in a quantum computer? We understand that this is the hardware that is present. And now we want to run some algorithm on this computer. How do we run it? And what functional designs are needed for such designs? Let's move on. So this is an overall scenario. Although this is the overall scenario, we will look in details specific to all these things. You have already seen many of the quantum algorithms in detail in last 2 days talks, right? And in all those details, what Dr. Sahu said in the last talk is that there is something called an oracle, right? And that oracle, we need to realize it using some reversible gates or functions, anything you can say. So if you see from quantum algorithm, he has shown how you will go to quantum circuit. But in between these two, there is a problem which one can solve. And that is, how do we realize a reversible function? Right? Because that oracle he was talking about, where you have quantum algorithms, you have other things, in between that reversible function we can realize using reversible gate, and which can be even for higher number of inputs also you can go. That is what is there. But all those higher level gates must be boiled down into quantum circuit or quantum gates, right? So all these quantum circuits in the morning you have already seen, those all are considered as logical gate. The X gate, the Y gate, the Z gate, T gate, Clifford plus T, NCV, all those constitute the logical gates, okay? Now what we call it physical gate, you recall what Dr. Kolhe has shown. For those simple logical gates, when you see that how it is being realized in that machine, in that IBM QX machine, it is boiling down to some physical gates. Some rotation gates were there, right? So all those are the physical gates, the way it is implemented in the IBM QX machine. And finally, on what all these gates are operating, I have already told you, on qubits. On the qubits you are having, which have certain, orientation based on which everything is getting mapped there. So is this flow clear to all of you? I know that the participants are not interacting much. but I would request that please ask queries, and then only you will be able to understand this problem and identify some research problem for your own research. Okay, now boiling down to this overall scenario, I will move to detailed workflow. Now, what is there in this detailed workflow? In this detailed workflow, we have seen today that how for Grover's algorithm, from the quantum algorithm level, there are two parts. There is some quantum specific modules, and there is something which is called oracle, where we must identify the identification of function to realize that algorithm. Okay. And there were a lot of algorithms. He was talking about x bar, x2, right? He was talking about many such functions that you can realize using reversible gates. So there is still a possibility that there has been a lot of research on this reversible logic, but now we can, redefine that in terms of the requirement that we have for these quantum algorithms. The problem might be same. It is the reversible logic synthesis, but your inputs or the functions that you want to realize, typical to that algorithm, typical to Grover's algorithm, typical to Shor's algorithm, you can basically identify those. Once you identify those, then you realize it with respect to the same function for Grover's with different oracle functions, how it performs. Okay, so this is an important problem. Here, reversible logic synthesis is still alive. We were thinking that this reversible logic synthesis research on that has become obsolete. No, it has not. You can redefine that. You can use, there are many, many methods that have been already discussed in literature. You can pick up one, realize your function, put it in that oracle function, replace it with the gates Dr. Shahu had shown today, and then realize your function. So in this context, synthesize the function using reversible gate libraries comes into picture. And this research is old research, I will say, but always you can go ahead and think of what improvement you can do targeting these kind of functions for certain algorithms, right? So this is one very, very important problem that I think one can take up by understanding the synthesis methods that are there in literature for reversible circuits, apply them into this oracle function for any of these quantum algorithms and analyze how the results comes. So this is one task which anyone can take up now. But there are a lot of things which you can do after even you have synthesized a function. So once you have synthesized the function, then you need to convert them into, generate the quantum circuits using the logical gate libraries. What are those logical gate libraries? They are basically NCV library is one, and Clifford plus T is there. Clifford plus T is there. So in the morning, it was already discussed how you can map it to these libraries. Once you map it to these libraries, there are many ways to optimize it, right? So you can further do some optimization based on what you have realized from this reversible function to this quantum circuits. Once you get that, you do optimization again. You can even do optimization here if the result is not exact. And I'll show you with an example in the later. part of this talk, that there is a lot of scope of optimizing at every level. At this level, you have the scope of optimizing. At this level, you have the scope of optimizing. And once you already know that how these logical gates will be mapped using this physical gate, then you can even do some more optimization at this level as well. So at every point of time, you have ample opportunity of optimizing the generated circuit. So these are some of the tasks which you can take up right away, right? And run the quantum gates on real quantum computer. That's what we have done it in the morning. So once all these things are done, you can go ahead, run your algorithm on a real computer. Is this flow clear to all of you? Okay, then I'll proceed. Hope you are understanding it. Now let us see some challenges in the
Yes,
design
there
of
is a
quantum circuits.
message in the chat, ma'am.
Yes, Dr. Kola, anything? Okay, great. So let us now see some challenges in the design of quantum circuit. You know, when I say all these things, it looks like, okay, each of these blocks, we can do this very easily. But doing each of these things will bring us some kind of challenges. Why we are not doing directly from here to here? It is not easy to do it. We can neither do from here to here, right? And that is the reason why we are moving from here to here to here to here, and then finally to this machine. Okay, so what are the challenges? Let us look into the challenges in some detail. As I said, it is for larger functions. It is not possible to design the function using logical gates. And for that reason only, we use some intermediate representation. And that intermediate representation is reversible circuits. Of course, we will be taking some examples to make the things clear, where what we do, we generally synthesize the functions using reversible gate libraries. So if you see in literature, there has been work on this domain from 2003, it has started, till probably I can tell you 2015. There has been a lot of work on this, right? And after this, slowly, even I would say 2016 or 17 also people tried to do something. But once this IBM QX came in 2017, the entire flow of the research has moved to a different end altogether. Researchers are now trying to do something which is more relevant to real computers. That is why I'm saying we have all the methods available for reversible logic synthesis. All we need to do is that take up that for a particular algorithm, analyze it on a machine, analyze it in a simulator, because for very large analysis of function, which will not be possible in using those machines, right? So once you do that, you will be able to see that what challenges are there. And the most important challenges is error. Error is a big challenge in the design of qubits. You know, if you want to realize a function of 3 qubit, which is 3-bit function, even for this, we might see that for keeping this qubit, we require another 2 qubits maybe. So the challenge of error is even higher. So that is an entirely separate thing to look into. But of course, as I said, there is a lot of scope of optimization at every point. At every point you design something as that is not optimal, and it is not possible for doing to get optimal solution for larger functions, there is a scope of optimization, right? So the problem of synthesis is what? Given a high level function, the problem of generating set of equivalent quantum gate operations in an efficient way, which is definitely not very, very easy. So in that respect, what we do, we use intermediate representation, as I've told you from the beginning, which is reversible circuits. Okay, so let us move ahead. Before I go to the actual synthesis problem, where I will be doing the synthesis things and all, let us very quickly look into that. How do you say that one algorithm is better than other? How do you say that this circuit, I have designed this circuit and this circuit is better than the other circuit? So there are some parameters or some metric that researchers have used over the years. One of such metrics, we call it quantum cost. Okay. So what is quantum cost? Quantum cost is basically, if you can boil down, this is a Toffoli gate. All of you know this gate. If these two values are 1 and 1, then only whatever you have here will get flipped. If it is 0, it will become 1. If it is 1, it will become 0. For any other input, 0, 0, 1, 0 or 0, 1, there will be no change in the output. This is what is the logical representation of this Toffoli gate. Now, this Toffoli gate can be realized using NCV library using these 5 gates. Square root of naught and then C naught and again that inverse of that and then again a C naught and again a B gate. So when we say that quantum cost in this technology using NCV gate library, it is 5. Why 5? Because each of this cost we call it 1. So this was one of the way, and for all the reversible methods, this was the way that the researchers have used to estimate the cost of a circuit. So you see, in conventional computing, you say the delay, basically, right? It takes this much delay to execute it. In the same way, there is some cost associated with it, you know. So now, again, someone can redefine this whole cost with respect to IBM QX machine. Or someone can redefine this whole thing with respect to the Google's machine that they are building. So depending on the technology, depending on which technology you are going to have your circuit, you are going to implement that, you can redefine your cost. And people are also doing that. That is also something one can look into it and then find out the cost of these functions. How do you redefine the same function in NCV, in Cliff-40 and many other things? Hope this is clear to all of you. So this was the notion of quantum cost and this is how it was said. Lower the quantum cost, better is your realization. But as you know that with larger functions, the quantum cost increases. You've also seen this diagram. What this says that when we talk about realizing larger input function, suppose n equals to 3, n equals to 4, and we go to n equals to 20. So this will change. So this is n equals to 1, 2, 3. This is a 4 input, 5 input Toffoli gate, right? There are 4 controls and 1 target, right? Ultimately, when we break this from a function, you can directly say that either it is taking a 4 input function or it's a 5 input function, whatever it is. But for realizing that 4 control or 5 control gate, there are certain methods. There are certain decomposition methods, standard methods, using which you can decompose this circuit into Toffoli gate, 3 input Toffoli gate, right? And you already know the cost of this. What is the cost of this? You see this? In NCV domain, this is the cost. So you can replace that using those gates. And you will see that when you replace this particular thing with this gate, if you just replace this with that quantum gate, replace this with that set of quantum gates, the whole circuit changes. And there, I again say that there are a lot of works already have been done where you will see there is a scope for optimization. You can optimize those gates. There will be some gates which may get cancelled out. There are rules for it. There are techniques for it where such kind of optimization have been done. But I would rather say, instead of going into this, why don't you will go into the more, technology aware gates rather than taking NCV gate at this point. So this is again up to you to choose any of these topic and go ahead for your research. Now for this, we have also seen this. Now you see, if you have this realization of a higher input Toffoli gate, then you can again replace this Toffoli gate with this set of realization. And again, this set of realization, you can have it for any number of gates. And again, when you have that, there is a further scope of optimization. So you can further optimize that to a great extent. So you see that we design a circuit, we map it to quantum gates, and then we look for optimization. And finally, we can put that circuit in the real machine to run it, right? So this is what I was talking about, optimization of quantum circuits. So if you see that once you have generated the quantum circuit, so first step was what? In the first step, you have to generate that reversible function. From that reversible circuit, you generate Toffoli gates, reversible gates. Those reversible gates have their quantum representation. But if you see those set of quantum circuit or quantum gates, there is a high possibility that you can reduce the number of gate operations. You can also reduce the number of qubits. The number of qubits that you're using, there is a possibility that you can reduce it. And of course, as number of qubits decreases, your readability increases. But this is a challenge again. As you have heard from yesterday's talk of Dr. Day, he clearly mentioned to break that RSA, you require 4098 qubits. And you know, that is an actual figure, 4098. That figure will again go up, blow up, when you actually build the device because of the error, right? So there are a lot many challenges, but nevertheless, we can look into all these possibilities and look for possible solutions. Now, till this point of the talk, we have discussed that, yes, there are many research problems that we can identify from mapping a quantum algorithm to realizing that algorithm in a quantum machine. But in this whole step, there is one step that is called synthesis. And now I will be giving you example of two very old synthesis method. But you can take up those very old synthesis method and try to formulate something for the algorithms for which the functions, what kind of functions could be realized. You can use these methods, you can optimize the methods, because as I said, even if we synthesize any reversible circuit, we have scope for optimization, because optimal solution, getting an optimal solution is not possible for large functions. So what is synthesis? Synthesis basically is the design. Given a high level functional representation, what we do, We realize that function with a gate library. We realize the function with a gate library. Let's say you have a gate library. And what is that gate library? In that gate library, you can call it multiple control topology, MCT. What is MCT? Multiple control topology. So this is a topology gate. So using this topology gate, you can realize any 3 input function, right? But if you want to realize higher input function, what you need to do? You need to extend this. And you see, this is what it happens. This number of control increases and this can go up to n. So you can have an n bit MCT gate, right? N control MCT gate, multiple control topology gate. So this is your gate library. So this is your gate library. Given the gate library, given the functional specification, okay, what is your task? You have to devise a method using which, using this gate library, you can realize this function. That is your whole task. All right, let us see how we can do that. So high level reversible function is given. We generate the reversible circuit and then we can transform those reversible circuit to quantum circuit. So this is the flow. But for this, we either need some kind of functional representation. In this case, we will be using truth table. Okay, a reversible truth table. So now, I would request, I know this is a post-lunch session, but I would request all of you to take out your copy and do this. And if you do this, you will understand this, that how exactly a small function can be realized using reversible gate. So this transformation-based method is a very simple method where we start with truth table realization. Truth table.
I have a question.
Yeah.
Actually, there are all classical function are not reversible. So can you tell me in brief that how I can, if a non-classical function, I want to make it reversible, what are the approaches?
Okay, so if you have a non-classical function, like let's say adder, right? An adder has 2 input and let's say another input carry, and it will generate sum and your carry out, right? Carry in will be there, carry out will be there. Now this is a 3 input 2 output function in a general classical sense. But if you want to make it reversible, then you have to embed, right? You need some kind of embedding where you need to take another extra line to make the entire process reversible. So for all these things, there are standard methods out there, which is called reversible embedding of classical function, where you can use ancilla lines. Basically, you can add extra lines to make the function reversible. So if you see in the next, this is an entire exact reversible function because a 3 input, 3 output. But what I was talking about, it's a 3 input, 2 output function. To make it reversible, we have to add 1 extra line and maybe 2 extra line to make it fully reversible. So there are standard methods for that. You can use it to do it. All right.
Yes, ma'am. Fine.
Okay. So let us do this small transformation based method where we start with truth table realization of a function and iteratively tries to match the inputs of the outputs of the truth table. And how do we do it? By adding one gate at a time. So what I'm saying now, what is our reversible function? Our reversible function is a truth table. A reversible truth table which has got equal number of inputs and output. Equal number of input and output. You have seen a Toffoli gate? So if you see, this is a Toffoli gate followed by a NOT gate, and let's say followed by a C-NOT gate, and then finally followed by another Toffoli gate. So how many gates we are having here? We are having 1, 2, 3, 4. We are having 4 gates. The number of inputs is 3. The number of output is also 3. It is not unlike we have 3 input and 2 output function. It is a same number of inputs and same number of outputs will be there. Right? So you can represent easily that in the form of truth table. Using transformation method, what we are going to do is that we will be trying to match the gate from the truth table, from the final truth table that we want to realize. We will start to add one gate at a time and then we will come to the input. And what will be the input? The input is so if for a 3 input function, if you say it is like this, 0, 1, 2, 3, 4, 5, 6 and 7. 2 to the power n minus 1 basically, right? And in a Toffoli gate, it is what? 1, 2, 3, 4, 5, 7 and 6. So in the form of truth table, if you see, only the last 2 rows will be what? It will be like this. For 1, 1, 0, it will be 1, 1, 1. And for 1, 1, 1, it will be 1, 1, 0. And rest all will be same. Starting from 0, 0, 0, it will be 0, 0, 0 and so on till 1, 0, 1. It will be 1, 0, 1. Okay. So this is a reversible truth table. Now, how do you get this? There are methods. You can directly get it from there. Now, if you want to transform a classical method, you need to see that way, formula, how you can optimally do it. Okay, that you need to check. This is the first step. But you see, this method looks to be very simple, but it leads to suboptimal solution. What is suboptimal solution? Which is not optimal. That means for that particular function, a better realization also exists. So this is not optimal. And it is also, when you are using truth table, you know that in a computer, how many number of bits you can use using this truth table method, which is of course not scalable to a great extent. You cannot do 100 input thing. Let us take this example. Okay. Now this example, now what is this function? You see, this is, what is this? This is 2. This permutation is like this, 0, 1, 2, 3, 4, 5, 6, 7 and 8. I'm writing this row. And now corresponding to that, this is 0, 1, 0. This is 2. This is 1, 0, 1. This is 5. This is 0, 0, 0. This is 0. Then 0, 1, 1. This is 3. This is 1, 1, 0. So this is 6. This is 1. This is 4. I missed out something. This is 2. This is 5. This is 0. This is 3. This is 6. This 5 is 1. This 6 is 4. And this 7 is 7. So no 8 will be there. Right? This 6 is 4. So you see this is your truth table, right? Corresponding to 0th row, what is there? 0, 1, 0, 2. Corresponding to first row, you have 5, 1, 0, 1. Corresponding to 2, it is 0, 0, 0, 0, and so on and so forth. Right? Now what you need to do in transformation method, you have to realize this function. You have to realize this function. For realizing this particular function, you have to keep on adding some gate, reversible gate, and come to this initial position. That is what you need to do. That is a transformation method. How? You are adding each gate at a time and it is transforming to the next one by one. Right? So let's see this. Okay. Can somebody tell me, like, what will be the first step? You see, this is 0, 1, 0, and this is A, B, C. Okay. So if you want to make this 0, 1, 0 to 0, 0, 0, at this point, if you add a NOT gate, this will become 0, 0, 0. Isn't it? So the first step is line B should be inverted because we need to match it. We need to match one by one. So I have added a NOT gate. Now once you add a NOT gate, what will happen? All the B input, whatever B input it is having, you see all these values, the middle values, all these values will be changed, will get inverted. Right? See, all those values are now inverted. This 0 has become 0, this 0 has become 1, this 0, 1, and so on and so forth. Once you do this, you will understand this. Now see, now the next step is what you need to do. This is 1, 1, 1. You have to make it 0, 0, 1. Right? You have to make this 0, 0, 1. How will you make it? With a single gate, you cannot make it. You have to also should not change the first row. So what gate should be added such that you can change this 1, 1, 1 to 0, 0, 1. You can do this by adding probably 2 gates. 1 gate will not suffice. So what you can do, if you want to make it 0, 0, 1, you see, if you take 1 and 1 and you invert this line. So a Toffoli gate with control in A and in C. Let's see this. When A and C is 1, 1, invert B. Right? A and C. Here it is, if both are 1, then this will get inverted. And you see what will happen? The middle one will become 0. See? The middle one has become 0. But still it has not become 0, 0, 1. It is now 1, 0, 1. You have to make it to 0, 0, 1. How will you make it? Now it is simple. Now you can use a C0 gate over here. This is the control and this is the target. Then it will happen. See? Invert C when A equals to 1. A C0 gate will do. And once you do this, the second row will become 0, 0, 1. You see? Once you do this, the second row has become 0, 0, 1. Subsequently, with this change, the third row already matches. Third row already matches with this. That is good. Now, we have to change the fourth row. And in the fourth row, what you have to do? You have to make 0, 1, 1. For making this as 0, 1, 1, this is already 1. So, you have to change 2 bits, this as well as this. So, again, what you can do? You invert B when A and C is 1, 1. So when A and C is 1, 1, invert B because you want what? 1, 0, 1, 2, 0, 1, 1. So first you have to make this as 0. For making this as 0, you can make a Toffoli gate because these two are 1, 1. Invert this. If you do this, what will happen? This will come. See? It has become 1, 1, 1. And now what you have to do? Now you have to change this one. This should become 0. You can simply do it with another Toffoli gate. If these two are 1, 1, you change this, right? If these two are AB is 1, 1, invert this, another Toffoli gate. And the beauty of this is that once you do this, you see, ultimately all has matched. So what we have seen in this particular method is that although this method is a easy method, we keep on adding gates and we keep on transforming. And finally, from this initial position, we have reached this final position. What was the final position? Final position is the starting from 0, 1, 2, 3, 4, 5, 6, and 7. This is where we have reached. Using how many gates? 1, 2, 3, 4, 5. 5 such gates. This is a very simple method, as you have seen, but this is not at all optimal. A better solution for this exists if you go for an exact synthesis. And what is an exact synthesis? Exact synthesis to an extent is where all possible checks are already made to reach to a final solution. So that we know that all possible ways are checked for getting the solution. Anything at this point of time?
One question, ma'am.
Yeah.
Yeah, so what I've seen here is we have the input, which is ABC, and the output, which is the initial, I think, that is the input and the output. So what we are doing is we start with the initial and we end till we have match with the input. So why not start with the input and end up with the output? Is there any problem with that? Or some, I mean, we start from the output and we stop it when we match with the input. Then why not start with the input and end up with the output? Is there any problem with that?
Probably you can do that. That is not a problem. I have not thought about it why they have not do that, but that is also possible. You can start from there and this will be your final solution, right? So what you need to do is that there you have to fix it in this way, but here you are fixing it in an order, right?
I see.
You are fixing it in an order. So you are putting 0, 0, 0 and you are fixing it, right? So here, if you want to do it in the other way around, then you have to fix this 0, 1, 0. And you cannot change that 0, 1, 0. And then you have to move to the next one. So just doing the opposite one is better.
I see. I see. Thank you, ma'am.
Anything else? Okay, so with this, we see that all the matches and we have a circuit in hand. Now, if you have the function or the oracle that we have been discussing in the morning in some form of truth table, you can use this method to realize the function, right? So now I'll move to another simple method, and that will be the last method for today's talk. Another simple method of doing synthesis. Now there you have seen that the number of inputs and number of outputs are same. ESOP is a scalable approach. Why? You can think ESOP for doing any input, any output function, but with a constant. Here, you are using reversible gates, but the outputs that you get is separate. It is not combined with the input. So the total number of lines required will be, suppose your function is 5 input and 5 output, right? So for that, you will be requiring the total number of lines as number of inputs plus number of outputs. And of course, there is a lot of scope of optimization. And there has been many works on ESOP since 2007. I hope now there are not so much work going on, but till at least 2 years back also people have done a lot of things on ESOP-based synthesis. Let us see what is that. You know what is sum of product. This is exclusive OR sum of product. And you have already seen that Toffoli gate, what we are essentially doing. There we are actually getting exclusive or sum of the products only, right? So if you can represent your function in terms of exclusive or sum of the products, then probably there is a direct way of mapping that particular function to your reversible gate. Let us see this. This is an example ESOP file. Now, how do you generate an ESOP file? From a PLA file you can generate. I have given the information at the end of the slide. This is an ESOP. What is it? Dot I represent number of inputs, dot O represent number of outputs, and there are 3 product terms. This, and this. Okay. Now, how do you represent this? This is a 3 input, 3 output function. And there are 3 ESOP cubes. What are the ESOP cubes here? What is this? 1, 0, dash. This is x1, this is x2, and this is x3. If you consider this as f1, f2, and f3, so in f1, this particular cube is there, this particular cube is there. And you see what is this? This is what? This is x1, and what is this is 0. So x2 is in complemented from x2 bar. So you say this is x1, x2 bar. Similarly, for another one, you have 0 dash 0. What is 0? This is x1, x2, and x3. Both are complemented. So this is x1 bar and x3 bar. Similarly, you can get for f2 and f3. So this is how you actually get the ESOP cubes. But the most important part here is how do you map a ESOP cube? You see, the mapping is so straightforward. These are your inputs and these are your outputs. There are, as I told you, the total number of lines will be number of inputs. These are inputs and these are outputs. Okay. So how do you map it? You map it in terms of, this F1, this particular cube is there, and F1, this particular cube is there. See how it is mapping? It is for the first one. X, solid dot, that means this is in normal form. And 0 means negative control, which is in complemented form. This is uncomplemented, this is complemented. And where we are having this is at F1. So for this particular cube, for F1 output, we are directly mapping from the ESOP cube. This is your X and this 0 is mapped here. And you get this. Similarly, just see the next one. The next one is, you see, this is for F1, for F2. For F2, this is there. This is only one X2 in uncomplemented from. X2 in uncomplemented from, and it is happening in F2. And similarly, this one for F3. What is there? For F3 also, you see, this is there. This particular cube is also there for F3. And as this is also there for F3, so you have this particular gate for this one. This cube, it is mapped here. What is this? This is happening for F3. So for each of these, this one, this one, this one, we have mapped these 3 gates. And now for this cube, it is there for all the output. So you map it this way. So this is the same one. It is happening here, here, and here in all the 3 outputs. So you can see how easy it is, but it comes with an overhead. Here, the number of lines is more. The number of lines more means the number of qubits will be more. And in quantum technology, reducing the qubits is a major challenge. So although you can realize larger function using this method, but this method will be difficult unless and otherwise we have a stable quantum technology which is error free, which can realize for larger qubits efficiently. So those constraints will be there. So this is one method. And finally, I'll show you that there are optimization possible where you can do some kind of output sharing. Because you see that many of the cubes we are repeatedly writing. Instead of that, we can forward that using some kind of C0 gates. Okay, let us see this. The same cube we have taken, and just that a simple reordering has been done. This particular cube, which is happening for all, is brought in at the top for all F1, F2, and F3. The next one with highest number of output is brought in to the top, and then the next one. So we have just reordered the ESOP cubes. After reordering, we will now map it. And let us see how do we map it. We are first mapping the first one. Okay? And after you map the first one, we are mapping it for F2. Instead of mapping it for F1, we are mapping it for F2. And we will see that as we map it for F2, and then we are computing, taking the result of this F2 from here and getting the result for F1 as well, or this one as well. Okay. Is it clear that we have computed first for F2? From F2, we are taking the result. Why? Because it is there for F1 as well as for F2 and as well as for F3. So instead of doing for larger gates where the quantum cost will be more, we are doing it with the smaller gate. And then we next compute F2 again, because for F2, there is one more cube, which is this one. Okay. So we compute this. So F2 computation is done. Then you can take that from F2 and take it to F3, because F2 computation, once it is done, it is also there in F3. So this computation is also there, this computation is also there. Instead of doing it repeatedly, that we did it in the previous case, naive mapping, here you have optimized it by using another C0 gate for forwarding the result. Okay. And finally, the last for F1, because one more cube is left for F1, we execute it. And that's it. See, earlier, how many gates it was taking? It was taking these many gates, 1, 2, 3, 4, 5, 6, and although these are larger gates. But here, after doing some kind of sharing or reordering, we have seen that the cost reduces to a great extent. All right. So these are the two typical methods. One method we have seen semi-optimal result, but the number of lines are less. But this can scale and you can do for any 100 input, 200 input function, but again at the cost of the number of qubits increases rapidly using this method. But there are methods which can be used to realize larger functions. Now, how do you generate these ESOP cubes? There is a tool called Exorcism 4, which you can use to actually generate the exclusive or some of the product form ESOP files. And from those ESOP, you can directly map it to reversible gates. So this tool directly is suited for reversible logic synthesis. I mean, there is no tool directly there. So you have to use that, then convert it, and then write your own code to get the realization. This is how it goes. I just wanted to give you a brief idea that whatever we have talked about, how you can represent it in a computer, you can go to the site revlib.org where you will get all the real files. What is real file? This is a typical representation of a real file. You see, this is the first thing is the target. Okay. C target means this is only NOT gate. A comma C. What does it mean? A means whatever is in the front. If it is A, B, C, D, even any number of variables are there, all those are controls. And the final one is the target. Okay, so C is the target. So you see, A is the control, C is the target. So this is how you can represent a real file. So if you are interested to work on this, you can download the files from this Revlib. Okay, so this is how it is represented. So this is the total representation of this file. And as I told you, for this circuit, if you want to find the quantum cost, what will be the quantum cost? You see, this quantum cost is 5, this quantum cost is 5. And all these C0 gate and NOT gate, typically, in a very ideal case, the cost is 1111. So total quantum cost in most of the old papers, if you see how they have calculated using some method like this. All right. So Clifford plus T, it is similarly like this. So this particular thing gets replicated for those, and then the total depth will further increase. There are 2 Toffoli gates with other C0 gate and NOT gate. You have to check whether some kind of optimization is possible at some end or not, and then you can realize it. So these are some possible research problems that you may take up, because now we know that these quantum algorithms are so popular that what kind of various function you can build as an oracle and then analyze the total algorithm, how it performs for different kinds of oracles. Okay, this is one. Of course, there is always a scope of improving the reversible logic synthesis suited for these kind of algorithms. You can look into that details as well. And efficient mapping of logical gate to physical gate is also very, very important. So you can see that. So with this, I think I've come to an end of this talk, where I've talked about general problem of quantum computing, what it is, and then we have 6 talks in this track, how those talk relates to each other. And finally, I've shown 2 typical reversible synthesis methods that are there in literature, from where you can at least get some idea and go ahead and start doing something. Although I said that saying and doing for large function is easy, but when it comes to doing it in the real machine, there's a challenge. So thinking about errors at this point of time, error-aware design is very important. You can also look into that. So there are many such problems, which probably I think would help you to look for some possible research problem for your own research. Thank you.
Thank you, madam, for the nice talk. Participants, if you have any questions, you may ask.
Ma'am?
Yes.
I have a question. Like while synthesizing this function, so decomposition also become a very important aspect, ma'am? Like
Yes, definitely.
Okay.
Decomposition, because we are talking about larger functions, and those larger functions must be realized in some using some physical gates. You have seen that there are so many levels. So there are logical gates, there are reversible gates, then there are physical gates. So coming down to physical level is a very challenging thing. So a lot of optimization, decompositions are needed at every level.
Okay, ma'am. Ma'am, you have also talked about the like in the previous lecture also they have talked about cryptography like for the RS requiring around 4098 bits and all.
Yeah.
But the challenge here, I think, like the computation can be only done in one quantum computer. Like we cannot use more than 2-3 quantum computers to achieve a common problem like we have in classical computing, ma'am.
So you are talking about distributed problem.
Yes.
So
Yes.
to distribute the problem into. So look, the challenge is till now 79 qubit machine has come up, but you think of 4098. 4098 meaning for even 79 qubit machine, you cannot run a 79 qubit thing altogether because of this decoherence, because of this error. So you can realize much smaller function. So for those 5000 qubit machine, you may require even double of that qubits. I mean, we really do not know how much, depending on the errors that it will have. So doing it in a distributed way might not be a very good idea because you see, distributed means what? Again, it has to travel from one end to another, right? When we talk about transferring it through internet, it is something else. But two quantum machine talking in distance for communicating or for realizing a particular function may be even more challenging.
Okay, ma'am. Thank you, ma'am.
One question, ma'am.
Yes.
Yes, I've seen in the last slide that you mentioned about compiler.
Yes.
Yes,
So
may you kindly, sir, so here is, we need good compilers for quantum computers. So basically,
absolutely.
and here is, let's say, for example, if I have a small C program, I want it to run in a quantum computers. So basically, we need some kind of a compiler to translate it into reversible logic, which is an intermediate representation. And what is the roadmap for that? I mean,
Yeah. So now again, if you listen to the first slide, what I explained, that why we will run a C program, right? C
yeah,
program can be efficiently run in a conventional computer. Think of that you want to run some quantum algorithms and some quantum based things in a quantum computer, right? And you need compiler for that. So for knowing the compiler, you need to know that how those gates interact, that lower
yes,
level things. Ultimately, when you write compilers, you need to know that underlying architecture of your device that you know for a conventional computer, right?
yes.
So
So yes.
here it is the qubits. Here it is the qubits and the gates. Okay.
Yes. So my question is, for example, like if somebody would like to write a quantum program, then he obviously need a kind of a compiler that translate into some sort of what you call as reversible logic, which act as an intermediate representation. And suppose people who are writing compilers, how they will know? Like they need some kind of instruction set. I mean,
Yes.
some
So
kind of a
you have
standard,
to look
right?
into, yes, you have to look into two things. One is Qiskit. Okay. If you go to that IBM QX machine, there is a thing called Qiskit and also Quasm. Okay. That is Quantum Assembly Language Program.
I see. I see.
Okay. There you will be able to know the gates, the registers and everything. Okay. That
Okay.
is there. And from there, you will be able to know that how you can write the compiler things. Basically, there are a
Yes.
lot of works that are being done for the compiler. And IBM is heavily investigating on this for writing such kind of things.
Yes, so I find it interesting from these reversible up for
Yeah.
generate. So given a quantum program, we generate a reversible logic, and yes, good.
Yes.
Thank you, ma'am.
Thank you. Thank you so much for asking all these questions. Any other questions, please?
Okay,
Okay.
I think there are no so many questions. So, ma'am, thank you for the talk. And here is the token of appreciation from the university end. And here is the memento for you, ma'am.
Yeah.
Sorry, ma'am, actually, I forgot to share my screen.
No problem.
Sorry. Extremely. Is it is it, is it visible, ma'am?
Yes, it is visible. Thank you so much.
Here is the appreciation, and here is the token from the
Thank you.
university head.
Thank you so much.
Thank you, ma'am. Okay, and participants. So today we are end with this quantum
We
computing
have to
time. So
share the link for feedback, I guess.
yes. So feedback link I just shortly share with you in this chat box, and please fill it and submit by today actually. Okay.
And also, please, if you have any queries, please write to me in my email, kamalika.datta@gisuniversity.ac.in. And not only that, quantum compilers have a great future, because how somebody will run something there. So compiler plays a very big role. So if somebody would like to look into that, that will be really great. We can work together and see something if it is possible.
So please everybody ensure that whether you have received the feedback form or not.
Please fill up the feedback form. This is really helpful for us.
For us. Yes. Okay, thank you. So we'll meet tomorrow at 10 a.m.
And there is also one request to all the participants. You see, mostly you all are faculty members. So you also expect that in your class, the student should come in time. So I would really request you to come in time so that we can start the program in the morning at 10.
Yes, yes. And also, ma'am, there is a plan actually for taking some assessment at the final session of
On the final day of the examination for their certificates. Yeah, that is
Yes, yes,
necessary.
yes.
So we will be sharing all the slides with you by end of the day, so that you guys can look into the slides and prepare yourself. There will be very short questions, so you can see and you can prepare. Yeah, we will be sharing that.
Okay, ma'am, then we can leave and
Yeah, thank you very much for your attention here.
10 a.m. Thank you, all of you.